So quite nice and simple questions, 1 mark questions. But again, at A level, they're a little bit trickier than at GCSE when we just have these 1 mark questions. At GCSE, they're sort of quite nice. And these 1 mark questions, they can sort of be a bit trickier. So, for example, this one, which of the following mechanisms does not, and again, that's a really important word there, not occur in reactions of bromoethane? Really important that we notice the not, and it's bromoethane. So again, obviously, I've just picked out questions on halogenoalkanes. In an exam, you're going to have a mixture of all sorts of different topics. So you'll be like, okay, organic chemistry, you need to know that bromoethane is a halogenoalkane. So again, you'll hear bromo, you think, okay, well, that's a halogen. Ethane, that's an alkane, so it's a halogeno or haloalkane. So go, okay, it's a halogenoalkane. So we're dealing with a halogenoalkane here. So we've got a haloalkane here. Well, let's look at what they can do. Well, we know halogenoalkanes can go through eliminations because that's what we did yesterday. They can also have nucleophilic substitution. So they can either have part of them have the halogen substituted by a nucleophile, or actually we can go through that elimination process, which actually still involves nucleophilic substitution. So we know that neither of them can be the answer. We have radical substitution. Well, we did radical substitution the other day. Free radical substitution can occur in reactions of bromomethane because we can use it to make bromomethane, and then it goes to that propagation stage. So where the more bromomethane that's made, the more we can make, and it's that sort of propagation part. So we know it's not radical substitution. So therefore, it has to be electrophilic. Electrophilic addition, and that'll get you 1 mark. And that is because obviously we're not going to be adding an electrophile to this, obviously because of its polar bonds in there. It attracts nucleophiles. It's not going to attract electrophiles. So yeah, so that's our answer to that one. Then we've got question 4. Again, it seems quite simple. It's multiple choice, 1 mark question, but there is a little bit more information in it that we need to pay a bit of attention to. So which of these compounds that we've got down here can react with ammonia? So that's a really key word that we want to focus on. Can react with ammonia to produce propylamine. So first of all, let's look at what's interesting. Well, we've got ammonia. So we know ammonia can be used as a nucleophile. So we know that can be a nucleophile. So we know ammonia can be used as a nucleophile, and basically it's producing an amine. Well, we know when halogenoalkanes go through nucleophilic substitution, when it's ammonia as a nucleophile, it makes an amine. So we know then, we've got a nucleophile that's going to make an amine. Well, that reaction then needs there to be a halogenoalkane. It needs to be a haloalkane. So basically, whichever one of these is a halogenoalkane. GCSE, obviously, we wouldn't go into this detail of alkenes and stuff, but you would maybe like have a list of names of compounds here. You need to actually be able to pick it out from the display formula. So let's have a quick look. We've got a double bond in A, which means it's an alkene, so it can't be that. D doesn't have a halogen in it, so it can't be that. B has no H. Alcohol also doesn't have a halogen in it, so it can't be that. So yeah, it has to be C, and that would get you 1 mark. So yeah, they look very simple, but there is a little bit of nuance to them. There's quite a bit of skill to them that we need to just sort of look at. So question 6. Oops. Here we go. So we've got 2-methyl propan-1-ol can be prepared by reacting 1 bromomethyl propane with dilute aqueous sodium hydroxide. Now, what I've done to question 5, but never mind. That's me to get instructed. So we've got 2-methyl propan-1-ol, sorry, and that can be prepared by reacting 1-bromo methyl propane. So obviously we know straight away 1-bromo 2-methyl propane is a halogenoalkane. So we've got a halogenoalkane there. So what we want to do for this is we want to name and outline the mechanism for this reaction. Well, we've got 2-methyl propan-1-ol, that's a hydroxide. So that's what we need to know there. That's a hydroxide. Well, that's not a hydroxide. I'm skipping ahead by stage. That's an alcohol, obviously. So 2-methyl propan-1-ol can be prepared by reacting 1-bromo 2-methyl propane with dilute aqueous sodium hydroxide. Highlighted the wrong bit for our hydroxide. So that is obviously our nucleophile in this situation. So name and outline the mechanism that we use to make this reaction. So why do we know that it's not going to be elimination? Well, it's not elimination because we're doing this in aqueous sodium hydroxide. If that had been in alcohol, then that would be a elimination. But because we've got an alcohol being made, reacting a halogenoalkane in an aqueous sodium hydroxide, that means that then that has to be nucleophilic substitution. So, nucleophilic substitution. Or substitute. Yeah, it's right. Substitution. So that is going to be, so yesterday when I kept going, oh, you really need to make sure you know, and we state if it's aqueous, if it's found in aqueous solution or if it's in a alcohol solution, that is why. And that is because it depends on what mechanism's going on. So if I'll give you a question like this and someone could quite easily, if they don't know the difference between it being in aqueous or in ethanol, that they would then go, oh, it's an elimination. It's not elimination because it's an aqueous sodium hydroxide. So now all it wants us to do is outline the mechanism for this reaction. We don't have to draw every single stage of it, but I will draw you the main overview of what you need to do. And this is exactly all you need for the exam question. So basically, the first thing you need to do is draw out 1-bromo 2-methyl propane. So propane, we're going to have 3 carbons. Oops, we've got yellow, not helpful. Carbon, carbon, carbon. 1-bromo, so we've got bromine attached to the first carbon. Here, 2-methyl propane. There we go. So that's 1-bromo 2-methyl propane. Our nucleophile, as we've already said, is sodium hydroxide. So our hydroxide is going to come in here. Oops, that is massive. And that lone pair of electrons here is going to, going to a wrong place. It's going to come in and it's going to attack that carbon here. What we would often do, and I'm going to explain why I did this yesterday. So nucleophilic substitution in these situations, it is always OH, but sometimes you will see them, people write HO like that, and they will do that just because then you can show those lone pair moving across easier. Exactly the same, we've just swapped them around just to draw it easier. It's a bit of a weird thing that we do. So anyway, going to that carbon, and then obviously when those electrons go to that carbon, we get an increase in electron density around that carbon. That pushes those electrons between the carbon and the bromine on the carbon-bromine bond more towards the bromine, and then that bond is going to be broken and those electrons go to the bromine. So I'm going to talk you through on the mark scheme where you get the marks. So this question in total is worth 3 marks. So you get 1 mark to say nucleophilic substitution. You get the second mark for showing a curly arrow from the lone pair on the oxygen to the carbon of the carbon-bromine. And you get your third mark for showing a curly arrow from the carbon-bromine bond to the bromine there. And it has to be on that bond. Anything that you might put, if you had any extra arrows on sodium hydroxide or any additional arrows from bromine to anything else, you would then get marks knocked off. If you drew out the wrong reactant or wrong product, you would lose some marks there as well. So part B to this is a percentage yield question. I'm going to quickly go through this because this is stuff that we did ages ago, but they literally sneak these sort of questions in all over the place. So when 2 cubic centimeters of 1-bromo 2-methyl propane is reacted with an excess of sodium hydroxide, 895 milligrams of 2-methyl propan 1-ol, which is our product, were obtained. The density of 1-bromo methyl propane is 1.26 grams per cubic centimeter, and it asks you to calculate the percentage yield for this reaction, and that is 3 marks. So basically, we need to work out our moles of 1-bromo 2-methyl propane. So we've got 2 cubic centimeters of it. So this is our first thing that we're going to do. So let's pop that there. What we're going to do is we've got 2 cubic centimeters of it, and we've got 1.26 grams is the density. So we're going to multiply 2 by grams. So that, and then what we will do with that is that answer there, which would be, I should be able to do this on the top of my head, but it's that sort of maths where I will get it wrong if I try and do that on the top of my head. I know I'm just doubling it. 2.52, and basically then that 2.52, we are going to divide that by 136.9 because that's our MR. And that will give us 0.0184 moles, and that is of our 1-bromo 2-methyl propane. Okay. So I'm just going to do that one in green just to make it easy so I don't have to keep writing them out. So next thing we're going to do is look at the mass that we're going to expect to have of that. So this is our moles of it. I'm going to carry on the green for now. So we've got 0.0184 moles of 1-bromo 2-methyl propane. And we are going, oh, have I got my 8 there? That is an 8, but it's written badly. So we're going to work out the mass of our 2-methyl propan 1-ol that we're going to expect to get. So, oops, don't know what that is. So we're going to multiply our moles here by our MR for 2-methyl propan 1-ol. So actually I'm going to highlight that in red so we know we're talking about that one now. So 0.0184, which is our moles, we're going to multiply that by 74.0, and that will give us 1.36 grams. So that is our expected grams for 2-methyl propan 1-ol. Okay. Last stage for this now is to look at our percentage yield. So basically, percentage yield, all we need to do to calculate percentage yield, let's do that in a different color. It would work. Here we go. Percentage yield, let's recall that equation. Percentage yield is going to be 100 times by 0.895, which is our actual yield. This is our actual yield here. This is what we actually got, 895 milligrams. Our expected, so our theoretical yield was 1.369 grams. So we need to convert 0.8, we need to convert 895 milligrams into obviously grams. So that would be 0.895. And we're then obviously going to divide that by 1.36. And the answer to that then would be 65.7%. So our percentage yield would be 65.7%. So I'll run through that quickly again. So first of all, we work out how many moles of what 1-bromo 2-methyl propane. So our halogen, alkane is how many moles of that we've got. We use the moles of that multiplied by our MR of our product to get our expected, our theoretical yield of the product. And then obviously we use our actual yield divided by our theoretical yield, times that by 100, and then that will give us our percentage yield, which was 65.7%. So when 1-bromo 2, and this is still the same question, it's the next part of it. So when 1-bromo 2-methyl propane reacts with hot concentrated ethanolic potassium hydroxide, so there's a few interesting things we want to focus on. I want to focus on straight away that we've got our halogenoalkane there, going to react with hot concentrated ethanolic potassium hydroxide rather than dilute aqueous sodium hydroxide. A different product is formed. Name this organic product and name the mechanism for this reaction. Gives you space to draw the reaction. You don't need to draw the reaction. You can literally just write it on. So obviously, this is an elimination reaction. Elimination mechanism even. And that is because obviously when we're using that ethanolic, the ethanol with the potassium hydroxide, elimination reaction occurs. And the organic product we're going to make there is, remember, when we do elimination, it makes alkenes and water. So our organic product we're going to make there, because we don't need to include water because that won't be an organic product. Our organic product we're going to make is a alkene. And so 1-bromo 2-methyl propane, well, we get rid of the 1-bromo because obviously that's going to go in the elimination process. So it's just going to become methyl. Have I missed? Oh, I've got Y. Propene. That would be our organic product. Another quick question here. Which species could act as a nucleophile? This is making sure you know, basically, your nucleophiles. If something's got, we're looking for the charges. Well, we're not looking for charges, but we know straight away if it's got a positive charge, it's not going to be that. So we know it can't be B. And we're going to look for ones that are going to have lone pairs of electrons. It's not going to be A because they don't have lone pairs of electrons, or D, so it's actually C. Have I got any more on here? Have we got to the end of the questions? Yes, we have. So let's get started on alkenes. That last question actually led us quite nicely on to where we're going to start. It will load. Yeah, looked at alkanes, looked at halogenalkenes, and look at alkenes. Nomenclature again, so naming alkenes, going to go through this part really quickly because it's the same sort of rules that we've talked about before. So we're going to look at what are alkenes and being able to name alkenes. So alkenes are a homologous series of hydrocarbons. Hydrocarbons are any molecule that only contains carbon and hydrogen. And they have the general formula CnH2n, and all the names end in -ene. So, for example, oh, no, we're not getting it for example. We'll say another part and then I'll show you one. All alkenes contain that carbon-carbon double bond that I was talking about quite a bit the past few days when we've done alkanes and halogenoalkanes. So alkenes contain a carbon-carbon double bond, and so they are unsaturated. So they're saturated if we don't have a carbon-carbon double bond, and they're unsaturated when we have that carbon-carbon double bond. And they have at least one carbon-carbon double bond. They could have more than one. So here we have an example. So number of carbon atoms, the molecular formula is C2H4. And as you can see, each time the number of carbon atoms increases, we just add an extra, we do H2N for then our hydrogens. So the names, if we've got 2 carbons, it's ethene, 3 propene, 4 butene, 5 pentene, 6 hexene. So as you can see, they're almost identical to alkanes, but instead of it being ane, it's ene. So alkenes with 4 or more carbon atoms display positional isomerism. And that's because the carbon-carbon double bond may appear between different carbons. It might not always be between the same carbons. So if there are 2 or more possible positions for the double bond, we use a number before the ene to indicate where that first carbon is involved. So for example, they would both be butene, but the first one is but-1-ene because that carbon-carbon double bond is on the first carbon, and we always describe it as the first carbon we get to rather than at the second carbon. So but-1-ene because the double bond is at that carbon, and this one would be but-2-ene because the double bond starts at the second carbon. So quick look at a couple of them. Here we go. We've got ethene, propene, but-1-ene, or but-2-ene. We can't have any others because if we had that double bond at this end, we would just number the carbons from that end as well. So we can only have 2 different positional isomers for butene. Got pent-1-ene, pent-2-ene, and that would be exactly the same for that. Hexene, we can have 3 different isomers, hex-1-ene, hex-2-ene, hex-3-ene, and again, that would then be the same if we worked from the other side. And that is a quick overview of them. So bonding in alkenes. So what is this double bond in alkenes? So all alkenes contain this carbon-carbon double bond. And it actually contains 2 different types of bonds. We just say it's a double bond to make life easier, but actually there's a lot more to it. And these double bonds are a result of an overlap of different atomic orbitals. So if we go back here, this is our alkene, it's ethene. And these are our atomic orbitals. And what happens is they actually overlap. The first type of bond results from end-to-end overlap of orbitals. So here we go, there's our end-to-end overlap of orbitals here, and we call this bond a sigma bond. Okay, and as you can see, that's our sigma bond there. And this first type of bond results from that end-to-end overlap of orbitals, and this occurs in a single carbon-carbon bond. So all single carbon-carbon bonds have that sigma bond. This is a sigma bond, and it is the strongest type of covalent bond. We obviously then have another type to make it a double bond. So the second bond results from the sideways overlap of atomic orbitals above and below the sigma bond, and we call this, both the top and the bottom ones, are pi bonds. So I'm going to go back here. They're pi bonds. Pi bond, its electron density is less than that of a sigma bond, so it's not as strong. What the pi bond does is the pi bond actually prevents rotation around the double bond. So all atoms will lie in the same plane. So the shape of ethene is planar, and the bonds around each carbon are at an angle of 120 degrees to each other. So we can see that here. So the main important things to take away from this is it's made up of the sigma bond, which is between the two carbons, and then above the two carbons we have those pi bonds. Those pi bonds prevent rotation around the double bond, and that means all atoms then are going to lie in the same plane, makes the shape of the molecule planar, and each of the bonds around each carbon is at an angle of 120 degrees to each other. So isomerism in alkenes. Rotation around the double bonds in alkenes is actually restricted because of that pi bond. And this can lead to EZ stereoisomerism, which is something that we looked at before Christmas. So here's two examples. So we have E pent-2ene and Z pent-2ene. The two EZ stereoisomers have exactly the same structure, but the arrangement of their atoms in space is different. The Z isomers have the two higher atomic number atoms attached on the same side of the molecule, whereas the E isomers have the higher atomic number atoms diagonally opposite each other in the molecule. So you can see that here. The Z have them on the same side of each other of the bond, and these ones have them diagonally. So a few quick questions about alkenes. So alkenes are a homologous series of hydrocarbons, and they have the general formula CnH2n, nothing fancy. They contain a carbon-carbon double bond, so therefore they are referred to as unsaturated. The double bond consists of a something bond and a pi bond. That is a sigma bond and a pi bond. The pi bond results from the end-to-end or sideways. It's not the end-to-end because the end-to-end ones is the sigma bond. It's the sideways overlapping of atomic orbitals that does the pi bond. So the pi bond results from the sideways overlapping of atomic orbitals and prevents that rotation around the double bond. The shape of the atoms around the double bond is planar, and the ability to rotate around the double bond, inability would make more sense. The inability to rotate around the double bond means that some alkenes display EZ stereoisomerism. So that is a first little look at alkenes. So addition reactions. Again, you're going to start to see lots of things that are starting to become quite similar. Organic chemistry is like that. We get lots of similarities between all of the groups. So we're going to look at what double bonds and electrophiles are, understand what addition mechanisms are, understand what hydrogenation is, look at how to test the alkenes, and learn about the structure and stability of carbocations. So electrophiles, we've talked about nucleophiles with alkanes and halogenoalkanes. Now we're looking at electrophiles. So alkenes are more reactive than alkanes. And this is because the bond enthalpy of the pi bond is significantly lower than the bond enthalpy of the carbon-carbon single bonds and the double bonds. So it gives them actually that extra reactivity because of having those pi bonds present. The double bond of an alkene is an area of high electron density. So we've got loads of electrons there. And therefore, it's actually an area of really high negative charge. So you can sort of see where electrophiles might come into play here. So the negative charge of that double bond could be attacked by an electron deficient species, which will accept a lone pair of electrons, which are called electrophiles. As you've probably guessed, they're the exact opposite of a nucleophile. So halogenoalkanes, they have that area of high positivity because of that polar bond. So they attract a nucleophile. Alkenes are the opposite. They have that high amount of negative charge because of the high electron density. So they can be attacked by electrophiles. These species have either a full positive charge or a slight positive charge on one or more of their atoms. And we call them electrophiles, and it means they're electron loving. Alkenes undergo addition reactions when they're attacked by electrophiles, and we call this electrophilic addition. So again, the exact opposite of our halogenoalkanes, which was nucleophilic substitution. So electrophilic addition, mechanism 1, let's look at it. So first stage of electrophilic addition, we're going to just start off with ethane here. So the positive charge on the electrophile is going to be attracted to that electron density in the double bond. So basically it's going to be attracted to this region here. And that's going to be our electrophile that's attracted to that region. Here's our electrophile. We haven't used a specific one, we've just put AB here. And remember, it's addition. So what happens is, as the electrophile approaches the double bond, electrons in the AB bond, which is our electrophile here, are repelled towards B. So they are repelled towards a negative charge in the electrophile. And the pi bond breaks, and A bonds to the carbon, and that forms a carbocation, an ion with a positively charged carbon atom. The two electrons in the AB bond move to B, and they form a B negative ion. That isn't the end of it. So that's the first stage. First stage, electrophiles attracted to here. Electrons break the pi bond, go towards the A here. The A is taken in by the carbon and bonds with the carbon. The AB bond breaks, and the electrons go from the AB bond to the B. And we then get the B ion and a carbocation. So that here is a carbocation. So the second stage of electrophilic addition, so we haven't finished there. Our B ion now acts as a nucleophile. It basically has the same sort of structure nucleophile. We've got a lone pair there, and it's got a negative charge. And what it can do is it can attack the carbocation. The lone pair of electrons on the B ion are going to be attracted towards the positively charged carbon in the carbocation, and that causes B to bond to it. So actually that whole electrophile has now, in two stages, bonded fully to our alkene. So what is hydrogenation? I'm just going to actually have a quick look and see if I've got another diagram of that just to show it you in a bit more detail. That's the structure of alkenes. Don't want the structure of alkenes. Oops, no, didn't I do that? isomerism. Here's an electrophilic addition of hydrogen bromide. Have I gone past it? Here we go. Electrophilic addition. So again, we've got that carbon-carbon bonding there with the sigma bond end to end, and then the overlapping creates the pi bond. Okay, and then we have the electrophiles. So the species that are tactical electrophiles, they possess a positive or partially positive charge somewhere in their structure. So they're going to have a polar bond. So that then obviously is our electrophile here. So the electrophile, which has some positive character, is going to obviously be attracted to our alkene. The electrons in our pi bond, and remember we need to say that it's in the pi bond, come out and they form a bond to the positive end on the electrophile. So that is our curly arrow to the electrophile. Because hydrogen can only have 2 electrons in its orbital, its other bond breaks heterolytically. The H attaches to one of the carbon atoms. So here we go. Got that happening here. We've now got a carbocation being formed, and that's our carbocation. This species now, the species that is left now has a lone pair, and it acts as a nucleophile and attacks the carbocation using its lone pair to form a covalent bond, and we get this being formed. And overall, there is addition. So an example here would be electrophilic addition of hydrogen bromide. So we've got ethene and hydrogen bromide. The hydrogen is going to be our positive charge here. Pi bond gets broken because it's attracted to the positive charge of the hydrogen. The hydrogen bonds with the carbon, and we get our carbocation being formed. We get that slightly positive charge. Our bromine is now acting as a nucleophile bromide ion. That's going to attack here at our positive charge on our carbocation. That forms a bond, and then we end up with bromoethane. Bromoethane, because we've got rid of that double bond. Oh, hang on. Bromoethane, that's a haloalkane. So I don't know what's happening. So hydrogen can be, so we're going to have a quick look at hydrogenation now. And so hydrogen can be added to that carbon-carbon double bond. And we could do that by using a catalyst, a nickel catalyst in a process called hydrogenation. So, for example, ethene plus hydrogen. So vegetable oils are unsaturated and may be hydrogenated to make margarine, which has a higher melting point. And that's why we do it. As well as a nickel catalyst, this requires a temperature of 200 degrees and a pressure of 1,000 kilopascals. So we need quite a lot of things. It doesn't just happen easily. So how could we test for alkenes? The presence of unsaturation, which is a carbon-carbon double bond, can be detected using bromine water. And bromine water has a red-orange coloured solution, and it's a red-orange coloured solution of bromine. A few drops of bromine water are added to a liquid and we shake it. If we have a carbon-carbon double bond present, the bromine adds across it. So it basically goes through electrophilic addition, and so then the solution will turn colourless. Now here's a really simple equation for the bromine water test with ethene. So we have ethene, we have the bromine and the water, and then this is what we get. However, because water is present in such a large amount, a water molecule which has lone pairs also adds onto one of the carbon atoms, and that's followed by the loss of a hydrogen ion. And so actually the major product of the test is not 1,2-dibromoethane, which is what we drew at the top here, 1,2-dibromoethane, but actually 2-bromoethanol. And that's just because we have water in such a high quantity. So electrophilic addition reactions, we're going to just have a quick look at some. So we can react to ethene with bromine, and that forms bromoalkanes by electrophilic addition. So if we quickly talk through this, like I showed you a minute ago, because that bromine molecule has no permanent polarity, but as it nears the alkene, the electron density in the bromine is repelled towards the bromine atom furthest away from the alkene, we get a temporary dipole. So then that temporary dipole, the positive end of that, the electron density in the double bond in the ethene, it attacks a slightly positive charge of the closest bromine atom, which will then act as an electrophile. This causes the bromine molecule to split by heterolytic fission. A bond forms between one of the carbon atoms and the closest bromine atom, forming a carbocation and a bromine ion. And then finally, the lone pair of the bromo ion attacks the carbocation and bonds to the other carbon and forms a 1,2-dibromoethane, which is a bromoalkane. Hydrogen bromide is that one that we just looked at a minute ago. Works exactly the same. It's always a polar molecule, so the electron density in ethene attacks that positive charge in the hydrogen atom. Bond forms with the hydrogen. Bromine attaches there. And we can also react with sulfuric acid. Sulfuric acid is a polar molecule, so the electron density in the double bond in ethene attacks a slightly positive charge on one of the hydrogen atoms. Again, it's attacking the hydrogen, and that's going to act as an electrophile. Bond forms again between one of the carbon atoms and the hydrogen atom, so we get that carbocation and a hydrogen sulfate ion. We usually write it as HSO4 ion. Then obviously that hydrogen sulfide ion is going to attack the carbocation and bonds to the other carbon atom, and it forms ethyl hydrogen sulfate. If we then warm ethyl hydrogen sulfate with water, ethanol is then formed and sulfuric acid is regenerated. And that's obviously because of that excess of water in the heat. So what happens if we do an electrophilic addition reaction to an unsymmetrical alkene? So when an electrophile, so let's use hydrogen bromide, for example, attacks an alkene with 3 or more carbon atoms, so we've got an example here, propene, a mix of products is formed. This is because the alkenes are symmetrical, so we're going to get isomers being formed. Very similar to when we're saying when we're going to form alkanes, we get isomers being formed. It's not that useful. It's useful, but then we have to try and separate them, which is hard, so it's not the best. So minor product, we could get 1-bromopropane, or our major product, we could get 2-bromopropane. Unequal amounts of each product are formed due to their relative stabilities, and that's because of the carbocation intermediaries. So let's have a quick look at carbocations. So if we're talking about them being stable or unstable, let's have a look at what they actually are. So a carbocation has a chain of carbon atoms, and they can be represented by R when drawing organic substructures. So this is an alkyl group. So we can have a primary carbocation, so they only have one alkyl group attached to the positively charged carbon. We could have a secondary carbocation, have 2 alkyl groups attached, or tertiary has 3 alkyl groups attached to a positively charged carbon. Again, very similar to the primary, secondary, tertiary halogen or alkanes. So the stability of these carbocations. This stability actually increases as the number of alkyl groups of a positively charged carbon atom increases. So basically, a tertiary carbocation is going to be more stable than a primary. And this stability increases because alkyl groups contain a greater electron density than hydrogen atoms. That density is going to be attracted towards and reduce that positive charge of a carbon atom, which has a stabilizing effect. So, and if we go back, so then depending on the stabilities of them is which ones we get more or less of. So structures of carbocations, which ones are primary, secondary, or tertiary? So we're looking for those R groups on them. So we've got an R group here, and we've got an R group here. So we've got a secondary carbocation. Here attached to this one, we've only got one group added. So we've got a primary carbocation. Here, again, we've just got a primary, so we've only got one R group here. Here, again, we've only got one R group onto the side, so we've got a primary carbocation. Here, we've got 1, 2, so we've got a secondary carbocation. Here, we've got one R group, so we've got a primary carbocation. And then finally, we've got 1, 2, 3 R groups, so we've got a tertiary carbocation. So are these statements about electrophiles true or false? Electrophiles all contain a lone pair of electrons. Well, that's false because that would be a nucleophile. The carbon-carbon double bond in an alkene is an area of high electron density. Well, that is true. The electrophilic addition to alkenes proceeds via a carbon cation intermediate. That is true. Bromine water can be used to test for unsaturation. That is true. And finally, if propene reacts with hydrogen bromide, the major product is propan-1-ol. Well, we would obviously be adding in that bromide, so it's not going to be propan-1-ol, so that's going to be false. It's going to be a halogenoalkane, so that's false there. So what is the time? 24. Let's have a quick look. At this question here. Yeah, we're just going to finish by having a look at this question. I'm just going to move it across to a different screen in a second. Okay, so I'm going to finish off with this exam question. I say this, but here we go. There's the exam question. Super, super tiny, so let's make it a bit bigger. Okay, so propene. Let's pretend we haven't just done a whole session on alkenes. So let's highlight this as we would. So propene, so we know it's an alkene, reacts with concentrated sulfuric acid to form two isomers, E and F. So the structure of E is shown. Name and outline the mechanism for the formation of E in this reaction. Well, we know that propene, when it reacts with concentrated sulfuric acid, is going to undergo electrophilic addition because concentrated sulfuric acid is an electrophile. So the mechanism is electrophilic addition. Move. There we go. So let's have a go at drawing this mechanism out then. So propene reacts with concentrated sulfuric acid. So the first thing we need to just do then is draw out propene. So propene, 3 carbons. Let's get them in. 1, 2, 3. We know we're going to have a carbon-carbon double bond somewhere, so let's add that on there. And we're going to have hydrogen, 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 hydrogen. So that is our propene there, and it's going to react with concentrated sulfuric acid. I'm going to just draw that in a different color. So let's draw concentrated sulfuric acid. Right, use that down. Sulfuric acid. So we've got our hydrogen attached to our oxygen, sulfur, double bond oxygen, double bond oxygen, OH. You do need to know the slave formula for sulfuric acid, so that is something to learn. So what is going to happen here? Let's have a look. Let's use a different color. Let's use blue. So the bonds are going to break. Well, that pi bond's going to break, and the electrons from the pi bond are going to be attracted to that positively charged hydrogen. So it's that hydrogen in the OH group on that concentrated sulfuric acid. So those pi bonds are going to break. Oops, and it would help if I drew this better. And they are going to go to the hydrogen here. The bond between the hydrogen and the oxygen is going to break because of that. And those electrons from the hydrogen and oxygen are going to go to the oxygen. Okay, so that is the first part. Then obviously we have the nucleophile made. So this sulfuric acid minus the hydrogen is going to become a nucleophile. So let's draw that out. So then we would have O minus with our lone pair of electrons. I know you must always include that lone pair of electrons. Everything else obviously is going to stay the same. Make sure you're drawing your arrow to say that's the next part of the mechanism. Oops. OH there. Okay, then we can just draw on what's happened. So we've had that addition of a hydrogen here to our propene, sorry. So let's draw that on up here. I'm going to actually zoom out a little bit so we can actually see the whole thing. So we have our carbon here. I never added, have I missed a hydrogen off this? Yeah, I missed a hydrogen off. There we go. So let's draw that out. So we've got hydrogen, 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 carbon, carbon. So we've not got that double bond anymore. That carbon's going to have a positive charge. I'm going to move its positive charge. I'm going to draw it underneath because I had my hydrogen above it before. Let's just pop its positive charge there. And then now this carbon obviously has now got 3 hydrogens on it because of the addition of it from here. So then what's going to happen is obviously that carbocation is, well, the nucleophile is going to be attracted to that positive charge from the carbocation. So then what will happen is from that lone pair of electrons, you need to draw it from that lone pair of electrons going to that carbon up there. It should just be a curly arrow, but I've drawn this really badly. But yeah, curly arrow going up to there. Go through where your marks are. It is a 3-mark question. So it's the last bit I'm going to do. You get your mark for saying it's electrophilic addition. No, it must be more than 3 marks. 5 marks. First mark for electrophilic addition. Second mark will show an arrow from the double bond towards the hydrogen atom of our sulfuric acid. So we've got one there. Third mark will show the breaking of a HO bond here. Mark 4 is for the structure of the correct carbocation. So you've got the correct carbocation here, and you must always include that positive charge there to make sure it's carbocation. That'll get you another mark. And then 5, you must show an arrow from the lone pair of electrons. That's why I'm making a big point about being on the lone pair of electrons, the negatively charged oxygen towards a positively charged atom of the carbocation drawn. There we go. So tomorrow we will